Good afternoon, or I guess still good morning to my HVACers. Oh wait, I went away from it. Today we are going to cover chapter 29, which is refrigerant system charging. So the objectives are: explain how to determine the correct amount of charge for a split system, discuss the difference between liquid charging and vapor charging, explain how to change systems that use zeotropic charge systems that use zeotropic refrigerants, determine the correct superheat for a fixed restriction air conditioning system using a superheat charging chart, determine the correct subcooling for a thermostatic expansion valve air conditioning system using a charging chart, list the variables that affect system operating pressures, define the AHRI standard equipment rating condition. So introduction: outside influences, balancing act, undercharging and overcharging. Low evaporator airflow due to dirt, improper fan speed, or poor duct design can mimic the pressure readings of an undercharged system. So what they're saying is the filter. If you have a dirty filter, then that can create undercharged conditions or create pressures that resemble an undercharged situation. The airflow across the evap coil is critical. The things that will ruin that airflow is dirt, like dirt on the coil, clogging it up, not allowing air to flow across the coil properly, or the filter, which is before the coil. And if that gets dirty and plugged up, then that's going to ruin your airflow. Or if your blower motor is not operating properly. I've had that happen before where the system was icing up and, customer thought that it was like a major issue. I mean, the iced up coil is a big issue, but it was just the capacitor for the blower motor. Changed out the capacitor, blower motor started running fine, everything was good. But when that motor is not turning and it's not bringing in that return air across that coil, then that refrigerant in that coil is 40-degree refrigerant inside of that evaporator box. So it's going to start to condensate on the outside of that coil. And if there's no warm air coming across that coil, that condensation is going to start to freeze. And eventually you're going to have an ice block in your evap coil, all due to the fan not spinning, because due to the fan not spinning, which is no airflow. So airflow is very critical on your evap coil, as well as your condenser coil too. I said it many, many times, but there's 3 mass fluid flows for air conditioning. There's the airflow across the evaporator coil, the airflow across the condenser coil, and the refrigerant flow. All 3 of those mass fluid flows are critical. If one of them are off, system won't perform properly. So the level of refrigerant charge is a delicate balancing act because too little refrigerant or too much refrigerant can reduce the system's performance. Some people don't realize it. I've had customers not want me to take refrigerant out when I diagnosed it as an overcharge, because they're like, oh, well, no, I want to keep my refrigerant. The more the merrier. That's not the case. It's not like the more refrigerant you have, the colder your system's going to be. There's a point, that you want to be at, and above or below that point is bad news. Undercharging can reduce oil return back to the compressor, cause high compression ratios, and lead to compressor overheating. Overcharging can cause liquid flood back to the compressor, leading to compressor failure. It will also cause liquid refrigerant to back up in the condenser, increasing the operating head pressure and reducing system efficiency. So both are bad. Both will kill your performance, over or undercharged. Leak testing. Check before charging. Always check for leaks if a system needs to be charged. Always check for leaks before evacuating the charging system, before evacuating and charging a system. So whether it's a brand new unit or a unit that you did repairs on, whatever the case, if you had to open the system and braze the pipes back together. Before you charge the system, you want to before you start your evacuation, you want to make sure you don't have any leaks, because that'll just be a huge waste of time, especially if you got other calls to get to afterwards. You don't want your employer to be on you about time management because you're missing little things. So whenever you open the system, air gets in, contaminants, whatever, non-condensable gases. So you got to pull all that stuff out. You don't want anything inside of the system but refrigerant. So once you braze all your lines together, your evacuation is important. But before doing so, you want to pressurize the system with nitrogen and check for leaks, because your evacuation is already going to be a time-consuming process. I mean, people ask me how long does it take. I tell them all the time it could take 5 minutes or 5 hours. It just depends, man. Depends on the condition of the system. Depends on your pump. Depends on the way the stars are aligned. I mean, it's a toss-up. It's a coin toss. But usually on brand new systems, on majority of my new installs, the evacuation half-hour max, on a brand new system. On older stuff, I've had more complications. But anyway, the point is you have to get to the evacuation. But if there is a leak, then your evacuation will take forever. You'll never vacuum that system down or evacuate that system to the level that you want. You want to get it to 500 microns. You'll never reach 500 microns if there's a leak, because all the pressure you're trying to pull out of the system, at the same time you're pulling it back in through the leak. So you'll be sitting there spinning your wheels for hours just to go back and leak check and find out you had a leak all along. So cover yourself, check for leaks before you start your evacuation and before you charge up a unit. Never be overly confident and just braze all your lines and just go straight to charging the system or straight to evacuating the system. Like, oh, I already know I don't have no leaks. I know I don't have no leaks. I never have leaks, but I check anyway. I mean, I'm that good. I don't have to check, but I check, because it ain't no time for mistakes. Ain't no time for cockiness. And it costs you money. Time is money. I think I skipped something. Oh, no, I didn't. So always find the leak. Adding refrigerant without finding and repairing a leak costs the customer money. The system will operate inefficiently by using more energy to produce less cooling. So that is a fact. You're losing money, or the customer's losing money, and you're losing credibility if you got to keep coming back and explaining to the customer why what you did didn't work right. Also, it's illegal to charge a system knowing that there's a leak anyway and just topping it off every so often. That's not what you want to do. You got to find the leak and fix it. If you can't find it, so the typical method, typically there's some refrigerant in the system. So you want some refrigerant because the electronic leak detector sniffs out refrigerant. So you want refrigerant in there, and then you want to add the rest of the pressure that you need to get it up to at least 150, 200 psi. You want to use nitrogen to charge it up to about 150, 200 psi. So you got nitrogen in there, you got some refrigerant in there. That's enough pressure to exploit the leak. Once you do that, take out your electronic leak detector, go along all the joints and everywhere you think that the leak might be, and then if it starts beeping, then you know you're in the general area. Then you pull out your soap bubble and you start squirting it in that area on the joints, and then boom, you squirt it on the right joint, and you see the bubble starting to form, and you know you found your leak. And then you repair the leak check it again, do your evacuation, charge it up, move on with what you got to do. But where was I? Always find the leak. Adding refrigerant without finding the leak costs the customer money. Oh, so what I was getting at was, so that's typically how you find the leak. So there are times, many times actually, where I've done that, did not find the leak. I mean, I spent a lot of time, kept looking, couldn't find it. So the ultimate way of finding the leak is to isolate both coils, meaning cut the inlet and the outlet pipes to the condenser, and then cap one end off and put a gauge on the other, and then do the same thing to the evap coil. cut the inlet and the outlet pipes, cap one, put a gauge on the other one, pressurize it, pressurize both coils and leave them overnight. Come back the next day, whichever coil lost pressure, that's the one that has the leak. And if neither coil loses pressure, then blame it on the piping. Because remember, the condenser is outside, the evap coil is inside. You've isolated both of them, neither one of them leaked, but there's still the matter of the piping that goes from inside through the walls or wherever it goes and then outside. So if neither one of those loses pressure, change the pipe that connected the two, and that will solve your problem. Liquid charging. Liquid charging is faster. System off on smaller systems, system on larger systems. Liquid charging chillers, low pressure chillers. So liquid charging is always faster than vapor charging because liquid is far denser than vapor, and taking liquid out of the refrigerant cylinder does not affect the cylinder pressure. Ooh, too far. On smaller systems, liquid charging is usually done with the compressor off. Prior to charging, the system must be leak tested and evacuated. On larger systems, a king valve located between the condenser and the metering device offers a convenient means of charging the system on the high side with compressor running. Low pressure chillers are charged through the evaporator charging valve. Liquid should not be charged into evacuated chillers or units with water-cooled condensers. Vapor charging on small appliances. Total system charge is a pound or less than a pound. Evacuate the system, introduce vapor until static, equalized pressure, factory specs. So equalized pressure meaning when you got your gauges on there and and the system is off and you're charging your refrigerant into the system. Once the pressures on that gauge, on your gauges start to equalize, meaning they're balanced out at the same pressure on both sides, on the high and low side, that typically puts you right in the ballpark. At that point, then you can fire it up and then start checking your superheat and see exactly where you are as far as your refrigerant charge. But personally, I don't think I've ever charged a system that small. Systems with a pound or less refrigerant in it are typically like window shakers, which are units that I don't really work on. I just swap them out if they go bad. And I guess some refrigerators have small amounts of refrigerant in there. Majority of my experience has been residential air conditioning and commercial air conditioning. So I'm dealing with, the smallest amount of refrigerant, on the systems that I've dealt with. I don't know, usually somewhere around 4 pounds at the least, maybe 3 pounds and some change. And then it just goes up from there. Anyways, vapor charging, heating the refrigerant cylinder. This raises the refrigerant temperature and pressure and allows the charging pressure to the charging process to continue. Vapor charging with unit operating. Most vapor charging is done with the compressor operated. So basically the pressure inside of the tank, once it gets low, it's kind of hard to pump that refrigerant into the system. So it'll seem like the cylinder is empty, even though it's not empty. It just needs a little help raising that pressure enough to push the gas into the system. So you can do that by, the best way to do it is to turn the compressor on. So once I charge a system and I get close to the mark, like let's say it's a brand new, or not even brand new, but let's say, it takes 3.5 pounds. So I put, almost 3 pounds in there. I get super close, and no more refrigerant wants to go into the system. But I know my tank's not completely empty. At that point, I'll go ahead and turn my system on and then continue to vapor charge it, because the compressor being on will literally suck the refrigerant out of the cylinder. because that's what the compressor does. It's a vapor pump. It's pumping the refrigerant, so it's sucking through the suction line, and then it's spitting out the refrigerant at a higher pressure out of the discharge line. So by the compressor being on and you're charging through the low side, which is the suction line, the compressor will literally suck the vapor out of the cylinder. Vapor charging. The pressure difference between the tank pressure and the system evaporator pressure will be greater as vapor is introduced into the low side. Charging zeotropic refrigerants like 410A. Refrigerants that fractionate, such as 410A, must be charged as a liquid. This prevents the separation of the refrigerant, because when it evaporates is when they separate, because it's a blend and they have different points at which they evaporate, or different temperatures. But when it's in liquid, it acts as like a solid, or a single refrigerant. Weighting a liquid charge into a evacuated system is the same with zeotropes as with regular refrigerant. In both cases, refrigerant leaves the cylinder as a liquid. Factors affecting system pressures: ambient temperature and airflow, which we talked about. We talked about airflow, inlet water temperature and condenser water flow on water-cooled condensers, return air, wet bulb and airflow, returning water temperature and water flow. So the major difficulty in checking system refrigerant charge by measuring any single aspect of its performance is that there are so many variables that can affect system performance. The high side pressure on an air-cooled system is affected by outdoor ambient temperatures as well as airflow across the condenser. So just like how we talked about airflow across the evap coil, or the lack of causing the evap coil to ice up, you have a different set of problems that happens on the condenser coil. So the condenser coil is where we're removing heat. So all the heat energy that was absorbed from inside in the evap coil has now made its way back outside to the condenser coil, where it will be released. The condenser fan's turning, and that refrigerant's moving through that coil. And as that fan turns, it sucks the cooler outside ambient air across the coil, and then it rejects it out through the top. So when that cooler air comes across that coil, the heat transfer takes place, and heat goes from hot to cold. So that hot refrigerant, the heat from the inside of that hot refrigerant is now absorbed into the ambient air, which is being blown straight out through the top of the condenser. That process can't happen if the condenser is clogged up with dirt, or if there's a lot of shrubbery and bushes around the condenser, which I've seen. And as that fan turns, like I said, it's sucking the air across the sides and it's blowing it out of the top. If you got bushes around the sides of the condenser really close to it, it's going to suck the bushes up against it. So now you have literally like a bush filter blocking the air from coming through and coming out of your condenser. So that lack of airflow, which is supposed to be used to cool that refrigerant, or not even cool it, but that airflow, that cooler outside air is what we're trying to use to absorb the heat in this refrigerant. If the airflow is not great or not good or adequate, it ain't gonna absorb any of that heat. Temperature goes up, pressure goes up. Pressure goes up too high, compressor shuts off on high head pressure. There's a high pressure safety switch on all your systems, and high pressure safety switch is going to trip because we're not removing any heat, and the pressure is getting excessively high in that compressor. And the safety switch is there to turn the compressor off before it breaks. So airflow is extremely important across the condenser as well. So the high side pressure on a water-cooled system is largely determined by the condenser inlet water temperature and the water flow. Condenser water flow has a large impact on high side pressures in water-cooled units. Return air wet bulb temperature has a big effect on evaporator temperature and pressure in air conditioning systems. The airflow across the evaporator in an air conditioning system is also critical. Again, that's one of the mass fluid flows. You got three: airflow across the condenser, airflow across the evaporator, and the refrigerant flow. Your three mass fluid flows, all critically important. Standard industry design and operation. Standard design conditions: condenser temperature, water-cooled condenser and evaporator temperature in ACs, new equipment, evaporator airflow and temperature drop, TEV, and fixed restriction superheat and subcooling. So there are system operating characteristics that have become industry standards through common use. The primary rating condition for AHRI listed unitary air conditioning equipment is 95 degrees outside, 80 degrees dry bulb, and 67 degrees wet bulb inside. Those are the conditions that the air conditioning system is designed to overcome. So with this 95 degrees outside, many of those who have AC are going to flip that AC on. And if it's 95 outside, it's probably close to about 80 inside, depending on, depending on, the conditions, how many people around, your insulation on your home. But either way, it's going to be hot in the house. Those conditions are what the condenser or the air conditioning system as a whole is designed to overcome, to be able to cool that 80-degree room down to a comfortable 70, 71. And to be able to reject the heat in a 95-degree outdoor ambient condition. So earlier when I was saying how we use the outside air to cool the refrigerant, and you're thinking, but if the outside air is 95 degrees, how is it cooling anything? But heat energy travels from hot to cold. So as long as the condenser temperature is hotter than 95 degrees, then that 95-degree air is enough to cool that refrigerant. So typically you want it to be 30 degrees above ambient. So let's get back to it. So equipment manufacturers have been designing equipment to operate with a 125-degree condenser temperature. So 95 degrees outside, compressor raises the pressure of the refrigerant, which then raises the temperature of the refrigerant that had already absorbed heat from the evap coil. That same refrigerant has now made its way back to the compressor. It was compressed, it was increased in pressure, and now the pressure goes up, temperature goes up. So now that refrigerant is a good 125 degrees, which is 30 degrees hotter than 95 degrees, which is enough for the heat to transfer from the refrigerant to the 95-degree outside air. And that's how we reject the heat. So moving on. At AHRI design conditions of 95 degrees Fahrenheit. So again, those are the conditions that they're designed to operate or to perform in. So most equipment manufactured today isn't designed to operate with 125-degree coil. Let me see. Water-cooled condensers typically operate at lower head pressures than air-cooled condensers. The common design for air conditioning evaporators has been 40 degrees Fahrenheit evaporator when the air flowing across the evaporator is 80 degrees and 67 degrees wet bulb, 50% relative humidity. So a good healthy system is going to have a 40-degree coil during the cooling cycle, and that 80-degree return air that's being sucked out of the room, it goes across that 40-degree coil. Heat energy transfers from hot to cold, so that 80-degree air is going to come out of the other side of that coil somewhere around a good 54 degrees, give or take. So new equipment designed for higher efficiency typically operates at a slightly higher evaporator temperature. Standard airflow across the air conditioning coil is 400 CFMs per ton. CFM is the measurement of the amount of air being moved, which is cubic feet per minute. That's what CFM is. This is a commonly applied standard. The temperature drop across an air conditioning evaporator is typically around 15 degrees Fahrenheit at the ARI design of 80 degrees Fahrenheit and 67 degrees for wet bulb. Expansion valve superheat settings. Expansion valve superheat settings vary with the design and temperature range of the system. The system superheat of a fixed restriction system varies widely with system operating conditions. Subcooling on most correctly operating refrigeration systems is between 5 and 15 degrees Fahrenheit. All systems should have some subcooling. And just a quick HVAC tip to take with you into the field: if there's no charging chart on a system that has a TXV metering device, your subcooling, your target subcooling or your default subcool is 10 degrees. If there's a charging chart on the unit that's legible and hasn't been all weather beaten and you can still read it, then go buy the charging chart. But if there is no chart, as far as subcool goes, you can default to 10, and that's usually, pretty spot on, pretty close to the target subcooling. Manufacturer charging charts. Red line, overcharge example. Blue line, correct charge example. Green line, undercharge example. So let's make this a little bigger, try to get familiar with this chart. So liquid pressure is over here, suction pressure here, outdoor ambient here. Okay, so, and this is for a 410 system. So 410A refrigerant on the high side at 350 degrees at 350 PSI is the normal pressure, is where you want to be on an 85-degree day. Also, oh no, actually no, that's not where you want to be. This is overcharge. So that pressure is a little high, and 160 on the low side. So this would be overcharged. So this is where you want to be on an 85-degree day. You want your head pressure to be just over 300 and your suction pressure to be 140. So if you have a chart like this and you have your gauges hooked up and it's 85 degrees outside, then and your low side says something pretty close to 140 and your high side says something pretty close to like 310. Let me see, 10, 20, 30, 40, 50. Yeah, so like about 310, 308. Then you know you're in the ballpark. You're pretty much good to go. Oh, I hate when I do this. Oh, it used to go all the way back to the first slide when I did that. All right, cool. I figured something out on accident. All right, cool. Checking system superheat. System must operate for at least 10 minutes. After any charge adjustment, repeat the test procedure, ensures charge is within the proper range. Basically, an adjustment means whenever you add or take out refrigerant, you want to give it about 10 minutes to see what your new readings are before you say it's corrected or not. If you're undercharged and you added half a pound, you want to give it about 10 minutes to take your next reading and see, are you on the mark or do you need to add some more? And I use my scale. I use my scale every time, all the time, because some cocky people that's been out there a while doing this, they like to eyeball stuff, but I don't have time to overshoot it or to undershoot it. So for me, like, okay, let's say for example, you were low, you added a pound. You added a pound because your scale said your tank just lost 1 pound in weight. It'll show you on the scale with a negative sign in front of it how many pounds you put in. It's just basically showing you how much weight the tank is losing. The opposite is happening if you're taking some out. If you have a recovery cylinder, then you take a pound out, your tank will gain a pound. It'll say 1 pound on there, and you've taken out a pound. So let's say I add a pound, and now my subcool is too low. I overshot it. Well, at least now I know, now I have a reference. I know that I was under before, I added 1 pound and now I'm over. So I'll take out half a pound, see where that puts me. Oh, cool, put me right where I need to be. All right, I'm good to go. Now, let's say I didn't use my scale. I just added some. I just opened up my gauges and counted to 10, and now I overshot it. So now I'm gonna take some out and count to 5. I mean, I don't know. Maybe that'll work, but I don't have time. I've done that before. I didn't have a scale, and I kept going over, under, and it was the most annoying experience. And I had a scale, but I didn't have batteries I didn't have any good batteries on me. My scale died. I didn't have no batteries on the truck. It was one of those kind of days. And so I was overshooting it, undershooting it, back and forth, chasing my tail. Finally got it in the ballpark and got out of there. But for me, I need my scale every time, all the time. It just makes life easier. Anyway, charging for proper subcooling. Thermostatic expansion valves. TEVs or TXVs, same thing, different abbreviations. TXVs regulate the refrigerant flow over a wide range of load and charge conditions. TXVs or TEVs try to maintain a constant superheat. This means the superheat method is not the best method for testing the charge in an expansion valve system. That's why you check subcooling on systems that use TXVs, because they fluctuate so much. And they do that to compensate for the load. What is the load? The amount of heat on the evap coil. If there's an excessive amount of heat on the evap coil, then that heat is going to make our refrigerant, our liquid refrigerant, boil off too quick. So the TXV is going to open up some to let more liquid in, so we don't boil off the liquid too fast. If we don't have a lot of heat on that coil, then the TXV is going to close a little bit and allow less liquid refrigerant into the evap coil, so we don't have too much liquid and then they don't boil off fast enough. We don't want it to boil off too quick. We don't want it to boil off too late, because if it doesn't boil off at the correct rate, then you're at risk of sending liquid back to the compressor, which is a vapor pump and not a liquid pump. And then if it boils off too quick, then it won't absorb enough heat, and you won't get the cooling effect that you're looking for. Checking system subcooling. System must operate for at least 10 minutes. After any charge adjustment, repeat this test procedure, ensures charge within the proper range. So same principles apply when you're checking subcooling as well. You want to give it about 10 minutes every time you make an adjustment. Give it time for the refrigerant to circulate through the system and pressures to balance out before you make any definite judgment calls, because you don't want to have to go back, oh, I thought it was good, but then 10 minutes later the numbers change, which they will. So give it some time. Patience is probably the most important thing to have as a technician. Just kick back. If you got one of those bosses that are jerks and they ride you super hard and micromanage, start looking for somebody that makes a little bit more sense, because they know, they were techs before, they know how it is, but they don't care. They want to apply pressure because they're thinking about money. And don't think about money, not when you first get out there. I know I'm off topic a little bit, but don't think about money. Understand that money's gonna come. Money is easy to make when you're valuable, when you have a valuable skill set. People will pay for that value. So as a tech, just take comfort in knowing that you in the club. You once you get that EPA license, you're in the club with all of the dudes that make money out there. But you can't focus on the money. You gotta focus on what makes you valuable, so that people will give you money to do this. So I'm always talking about the basics, which is being presentable, being clean every day, smelling good, looking good, clean cut. Even if you got a big old beard, keep it edged up. Whatever you're doing, look good. You make your tool bag look good, because that's how looking good on the outside is how you look good to the customer. Also, it's a professional appearance to your employer too. But what makes you look even more attractive to your employer is how good your tool bag look. Try to stay up on tools. Try to keep plenty of tools. Every tool that you possibly could need to make your job easier. Keep new ones if you can. I mean, when you start getting old and rusty stuff, upgrade. Don't be cheap. Upgrade. Don't throw away the old rusty stuff. I got crates of old rusty stuff. I just don't part. I don't sell no tools. That's smoker stuff to me. I keep all my tools because you're always gonna need backups. You might lose something or whatever the case, or somebody might want to borrow a tool. Give them the rusty one. So anyway, look good. Keep your tools, and then also be a lifelong student. Go to classes, get extra certifications. Just dive fully 100% into this, and it will 100% pay off. It's not a maybe like some things. You can study football your whole life and work out your whole life and never make a dime playing football. But if you study this stuff and you get your credentials, you would have to try to not make money. You're gonna make money. So anyway, let me get back to this part. So liquid ambient, and I don't even know where that came from. What was the previous slide? Check the system subcooling, proper range. I don't even remember how I got on that point, but whatever, take that with you. Excuse me. So temperature differences. The liquid line is always a little warmer than the outdoor ambient temperature. One second. Okay, all right, I'm back. So the liquid line is always a little warmer than the outdoor ambient temperature. The approach charging method examines the temperature difference between the liquid line and the outdoor ambient temperature. Calculating the approach. Measure the liquid line temperature and subtract the outdoor ambient temperature. Use the same thermometer to take both readings to validate accuracy. A few degrees difference can give a different diagnosis. Water-cooled systems. So they're giving you kind of a sequence to go through. So first check water temperature and water flow. If the water is too cold, you'll have low pressures, and it's going to give you the symptoms of an undercharged system. Too little water flow is going to give you higher than normal pressures, and it's going to give you the symptoms of an overcharged system. Oil charging, cleaning a system with multiple compressor failures, checking the compressor oil, changing the compressor oil. One of the fastest ways to clean a system that has experienced multiple compressor failures is to check and change the compressor oil. So anytime you have a compressor burnout, you're going to change the oil. You're going to, if you have a compressor burnout, you're going to change the whole compressor actually, and you have to flush the lines. But anyways, changing the oil is something done on larger equipment. You don't have access to change the oil on like residential equipment, like hermetic compressors. There's a way to do it, but it's not often done. It shouldn't even have to be done unless somebody contaminated it by putting like the wrong refrigerant in the system or something like that. In which case, yeah, you would have to change the oil. Oil charging, hermetic compressors. It is not practical to remove oil from a hermetic compressor. Hermetic compressors do not have crankcase ports. Semi-hermetic compressors are open compressors. Adding or removing oil is more reasonable with these compressors. Small semi-hermetic compressors have a crankcase plug above the normal crankcase oil level that may be used for removing or adding oil. So hermetic compressors are factory sealed compressors. They're welded shut. All their moving parts are inside of a welded closed container. And semi-hermetic compressors have heads that can be removed, and you can open up the compressor and work on them. And those kind of compressors have the plug above the crankcase, and you can actually change the oil on those. That's like a commercial and industrial task. Using vacuum to add oil. In the evacuation method, the compressor creates a slight vacuum that is used to suck oil in. Purge the air from the oil line by blowing a small amount of refrigerant vapor through it into the oil. So the same way how they're saying that you could put this system under a vacuum and then it'll suck the oil in, the same thing is happening when you're charging a system with refrigerant. Whenever you like when you have a brand new install, you digitally check already, and then you put it, and then you do your evacuation. You have it down to 500 microns. Well, now that pressure, that system is under a negative pressure. It's kind of like if you suck all the air out of a bottle and then put the top back on. The bottle's going to stay all scrunched up. As soon as you take that top off, it'll get its shape back because it's going to suck the air right back in. The system's doing the same thing. It doesn't get scrunched up because it's metal, but it's under a negative pressure. So the moment you open up the your lines, it's gonna suck the refrigerant right out of your cylinder. So anyway, in summary, a system that has been evacuated is normally charged with liquid into the high side of the system with the system off. The amount of refrigerant added is measured by an electronic scale. Always, always, always. I don't charge nothing without a scale. The amount and type of refrigerant used in a system can be found by looking at the data plate. Common forms of charging charts provided by manufacturers include charts that correlate operating conditions to system pressure, superheat, and subcooling. Superheat charts are used with fixed restriction systems, while subcooling charts are used with thermostatic expansion valve systems. Again, on systems that have fixed orifice or fixed restriction type metering devices, which include capillary tubes or a flow rater piston, those you're going to be checking by superheat because they maintain a constant superheat. The TXV systems, they change so much, and you're checking those by subcooling. So anyway, I hope that was helpful. That was chapter 29, refrigerant charging. What am I saying? FlexiQuiz. Chapter 29 is on FlexiQuiz already. Tomorrow's test day, so I will be sending out practice tests. I hope everybody's finding a way to stay motivated and to stay engaged. I apologize for my absence. It's been a little while since I've been able to do this. There's been some changes going on at the office and changes on the platform. And I am back on this platform for you guys' benefit. So I'm going to try to make a better effort at staying in communication. So I'm going to go ahead and get this sent out right away. Stay safe, stay in the house, stay healthy. We will be back sooner than later. They are making plans to bring students in during the stay-at-home order, and we're going to be bringing in a small amount of students at a time, a few times a week. So they're trying to put it together, a schedule and a date where we can start doing that. I don't know when that's going to start, but I'll give you the updates as I get them. But we will start bringing people into campus slowly. It's going to be like the first phase of getting back to campus. The first phase will be a hybrid where we'll still do the online stuff and then have a few days out of the week where you can come in and get some hands-on training. And then the next phase will be just back to business as usual, everything on campus. So like I said, I'm getting little tidbits here and there. I'm sharing them with you as I receive them. So I'll give you the next update when I get it. Until then, again, stay safe, stay healthy, stay motivated, and I will catch y'all on the next one.